Now, today class is nonlinear programming with inequality type constraints. In the last class, we learned about nonlinear programming with equality type constraints. Okay. Now, the heading is constrained multivariable optimization. Constrained multivariable optimization. Multivariable optimization with inequality constraints. With inequality constraints. Whenever equality constraints are there, we apply Lagranges multipliers method. Lagranges multipliers method. Now, to solve the NLPP with the inequality type constraints, maybe less than or equal to or greater than or equal type constraints, the method is named as Kuhn-Tucker method, Kuhn-Tucker conditions. Okay. Now, the thing is here, whenever a NLPP, nonlinear programming problem, involves inequality type constraints. Inequality type constraints. Inequality type constraints. Then we solve it by using. Kuhn-Tucker conditions. Kuhn-Tucker conditions. Kuhn-Tucker conditions, simply called as KT conditions. Simply called as KT conditions. Kuhn-Tucker conditions. Now, what is the problem now? So let us see the problem. Consider the NLPP. Consider the nonlinear programming problem. Optimize z equal to. Optimize, maybe maximize or minimize. Optimize z equal to f of capital X. F of capital X means what? Capital X means what? It contains n variables. It contains n variables, x1, x2, xn. So I will write here itself x1, x2, xn. F of x, nothing but f of x1, x2, x2. Subject to the constraints. Subject to the constraints. What are the constraints type? I told you. Generally, we consider less than or equal type constraints. Standard method is developed for less than or equal type constraints. Less than or equal 0. I equal to 1 to m means m constraints are there. G1 of x less than or equal 0. G2 of x less than or equal 0, and so on. And capital X greater than or equal to 0. And capital X greater than or equal 0 is nothing but what? That is, I will write. That is, capital X greater than or equal 0 means x1, x2, all the variables are greater than or equal 0. Non-negative restrictions. Non-negative restrictions. Capital X here, for your idea, X stands for what? The solution vector. X stands for what? Solution vector. Transpose. Nothing but what? It's a column vector. It's a column vector. Now, this is my nonlinear. This is our problem. This is our problem. Okay. Nonlinear programming problem with what type of constraints? Inequality type constraints. Less than or equal to type constraints. Less than or equal to type constraints. And to solve this problem, first already we know Lagrange's method with equality type constraints. Right? So the base is that one. The base to solve any LPP is Lagrange's method. That means convert the inequality type constraints to equality type constraints. Now, what is the type of inequalities here? Less than or equal to. As you know, to convert less than or equal to, I have to add slack variable. Slack variable on the left side of the constraint, right? So before that, as usual in Lagrange's method, what is our assumption? What is our assumption? GIX less than or equal 0. Here, what is GIX actually? GI of x is nothing but HI of x minus BI. HI of x BI. That is, constraints are like in Lagrange's method only. Constraints are hi of x less than or equal to bi. These are the original constraints. These are the original constraints. These original constraints are transformed to what? Gi of x taken as hi of x minus bi. So constraints becomes gix less than or equal to 0. This is the constraints part, gi of x. Now to convert, the next step is what? To convert less than or equal to type constraint. To convert less than or equal to type constraints to equality type constraints into equality type constraints, add slack variable, si I equal to 1 to m, that is m constraints are there, therefore we have to add m slack variables where all si greater than or equal to 0, where all the slack variables greater than or equal to 0. Now to avoid the condition, si greater than or equal to 0 for I equal to 1 to m means what? Non-negative. Means what? Non-negative. We consider squared slack variables. We consider squared slack variables si square instead of si. See, si greater than or equal to 0, and that means non-negative. Instead of this, we consider squared slack variable which are always non-negative, si square, which are always non-negative. For I equal to 1 to m, we consider, to avoid this condition, non-negativity condition, we consider squared slack variables si square I equal to 1 to m into the constraints. Then what are the constraints becomes? Then we have, what are the constraints? Gi of x less than or equal to 0. Now plus adding slack variable, this is equal to 0. So for I equal to 1 to m constraints are there. Why I am considering squared slack variable? Just to avoid this condition, si greater than or equal to 0. Si square stands for always non-negative. Then what is the problem becomes? Then NLPP becomes. What is the thing now? NLPP becomes optimize z equal to f of capital X subject to the constraints. What are the constraints now becomes? Equality type constraints. Now what are the constraints? Equality type constraints. I equal to 1 to m. And what are the non-negative constraints? Just x greater than or equal to 0. No need to write si greater than or equal to 0. Now the inequality type constraint problem is transformed to what? Now equality type constraints with the equality type constraints. Now whenever equality type constraints problem is there, I can solve using Lagrange's method. Hence we can apply Lagrange method. To solve the NLPP. This is the first logic. Okay, what is the first problem? We are considering non-linear programming problem with less than or equal type constraints. We don't know how to solve the problem, but we know the problem with equality type constraints. The method to solve, that is Lagrange's method. So I am adding a squared slack variable in the constraint part to convert them to equality type. Hence Lagrange's method is applicable. Then define Lagrange's function. Now let me define Lagrange's function. You know how to write Lagrange's function. L, the variables, all the variables are included in capital X, right? And what are the next one? Slack variables are there. So S is the slack variables. M slack variables are there, stands for S. And the Lagrange's multipliers are there. Okay, what is this function? Objective function minus Do you remember? I told you already. Lambda I into the given constraints. What are the given constraints? GI of x plus SI square. GI of x plus SI square. These are the Lagrange function. That means lambda 1 into g1x plus s1 square, lambda 2 into g2x plus s2 square, and so on. M constraints are there. So objective function plus sum of all the constraints multiplied by Lagrange's multipliers, where lambda I are the Lagrange multipliers. Lambda I are the Lagrange multipliers. And here, one by one, what is x, capital X value? You know, what is this x? It is a column matrix. So I will write transpose here, right? And what is the S matrix? It is also slack variable matrix, S1 square, S2 square, and Sm square slack variable matrix. Done. And next one, what are the lambda? Lambda is nothing but Lagrange's multipliers. M multipliers are there. Lambda is nothing but Lagrange's multipliers. Transpose. All are transpose. Now, what are the next one? What is the next thing in Lagrange's multipliers method? The necessary conditions. The necessary conditions to optimize. The necessary conditions to optimize L, Lagrange's function. To optimize L are, what is the first one? It's a L derivative with respect to all the variables equal to 0. L derivative with respect to all the variables. So x1, x2, xn. This is the first condition. And what are the unknowns actually? Unknowns are what? Unknowns are x1, x2, xn. Next, what are the unknowns? S1, S2, Sm. And next unknowns are what? Lambda 1, lambda 2, lambda m. All these are unknowns. So in first unknowns are over. This part is over. x1, x2, xn. What is the second one? This lambda. I will write lambdas first. Dou L by how many lambdas are there? I. M lambdas are there. So I equal to 1 to m. Partial derivative of L with respect to lambda I equal to 0. And another one is what? With respect to Si. Slack variables are also unknown. Okay. So this is equal to 1 to m. This is 1 to m slack variables are there. So dou L by dou Si equal to 0. 1 to m. Now, these are the necessary conditions. Necessary conditions to optimize L are these three. What are the necessary conditions? Always to get maximum or minimum. Lagrange's function partial derivatives with respect to unknowns equal to 0. Unknowns are xj's, lambda I, and Si. Now one by one, let me take. Now, dou L by dou xj equal to 0 implies. Now see this function. Is screen is visible? All of you? Is it clear?
Yes, sir.
Yes. Dou L by dou xj equal to 0. What is L? Is here. Dou L by dou xj means, see, I'm writing elaborately this. L of, one can write x1, x2, xn, s1, s2, sm, and lambda 1, lambda 2, lambda m. And what is this function? F of x1, x2, xn minus summation. This is as usual. There is no change here. And you can write x1, x2, xn plus si square. Okay, this is I equal to 1 to m. I equal to 1 to m. Now, L derivative with respect to xj. What is this? Wherever xj are there, I have to apply. That means dou L by dou xj is nothing but dou f by dou xj, dou f by dou xj minus lambda j into gj, dou g by dou xj. X terms are involved in g, right? So what is this is now dou f by dou xj. If any doubts, you can raise the questions. Dou f by dou xj minus, in lambdas, this is summation I equal to 1 to m. Okay, lambda I as usual, it is there. With respect to xj now, xj's are involved in what? G. So dou g by dou xj equal to 0. This is for j equal to 1 to n. Any doubts? Just I'm giving rough figure here. L is nothing but what? F of x1, x2, xn minus summation lambda I into gai of x1, x2, xn plus si square. This is bracket I equal to 1 to m. So with respect to xj derivative means what? F derivative with respect to xj, this lambda I as usual, and since g contains the variables, dou g by dou xj, dou gi will be there. I is here na, dou gi by dou xj equal to 0. Any doubts in this expression? Yes. Next one, dou L by, what is the next condition? Dou L by dou lambda I equal to 0. Dou L by dou lambda I equal to 0. Now see, this is the function, lambda I. Dou L by dou lambda I means, for example, if I take lambda 1, dou L by dou lambda 1, there is no lambda in F, so this part 0. What if I expand this summation, what I'm getting, minus lambda 1 into g1 plus s1 square minus lambda 2 into g2 plus s2 square, like this I'm getting, right? Okay, this is rough work. So if I take dou L by dou lambda 1 equal to 0 means what I'm getting, this part. If I take dou L by dou lambda 2 equal to 0, then I will get g2 plus s2 square equal to 0. So in general, what I'm getting, minus will be there. With respect to lambda I means what I'm getting, gi, right, of x plus si square equal to 0. This is I equal to 1 to m. M constraints are there. Any doubts? This is the second expression. Next one, dou L by dou si equal to 0. Now dou L by dou si equal to 0 means, where is si? Here. For example, dou L by, say, dou L by dou s1. Dou L by dou s1 means what is the derivative? In F there is no s, so 0. Now s1 is here, 2 s1, so minus 2 lambda 1 s1 equal to 0. Dou L by dou s2, then minus 2 lambda 2 s2 equal to 0. Like that we are getting. So dou L by dou si means what? What you are getting? Minus 2 lambda I into si. 2 lambda I into si equal to 0. This is I equal to 1 to m. Okay, these are the three necessary conditions. Now, one by one I have to evaluate. One by one I have to evaluate to simplify all these expressions and to get the necessary conditions. Okay, the first part. See, one by one. One by one. First one you consider. What is this last condition? Now, consider dou L by dou si equal to 0. First condition. Dou L by dou si equal to 0 gives what? Lambda I si equal to 0. Lambda I si equal to 0. That is either lambda I0 or si0. That is either lambda I0 or si0, right? Okay, these two conditions. Now, if si equal to 0, or if I take, yeah, you take this. First condition, lambda I is 0 or si0. Then you consider one part. What is that? If lambda I equal to 0, then si not equal to 0, right? Yeah, exactly. If lambda I equal to 0, if I take, just wait, to simplify these conditions, give me a minute. Lambda I si, right, done. Lambda si 0, done. So I have to get lambda into gix equal to 0, right? If si equal to 0, if si equal to 0, I am considering this part. First thing, if si equal to 0, then lambda I not equal to 0, correct? Lambda I not equal to 0. And I will write here itself. And if si equal to 0, let me give some equation numbers. All of you, this is 1, this is 2, and this is 3. Now, if si equal to 0, from equation 2, what this is, 0 means gix equal to 0. If si equal to 0, from equation 2, From equation 2, what I'm getting? GI of x equal to 0. GI of x equal to 0. Or if lambda I equal to 0. Or if lambda I equal to 0. Then what lambda I equal to 0 means what? If lambda I equal to 0, that is SI is not equal to 0, right? SI is not equal to 0. Please understand this concept. Lambda I equal to 0 I am taking, therefore SI not equal to 0. Then what this becomes then from equation 2, GIX must be what? It must be less than or equal to 0. Got it? Because I'm writing here, because SI square means what? Positive. SI square means what? Positive. Okay, greater than or equal to 0. Then 2 implies, what is this 2? GIX plus SI square is equal to 0. Okay, since SI square is greater than or equal to 0, to satisfy this equation, this GIX must be what? Less than or equal to 0. That is the idea. Once again, when lambda I equal to 0, that means SI not equal to 0. SI not equal to 0 means what? Definitely SI square or greater than or equal to 0. What is the second constraint? The second condition is what? GIX plus SI square equal to 0. Now SI square, I know this SI square are positive, and to make it as equal to 0, this GIX must be less than or equal to 0. This is another one. This is another one. Therefore, together what we have? Therefore, we have what is the first condition? SIX is when SI equal to 0, GIX equal to 0. When SI, this is SI not equal to 0, that means lambda I equal to 0. Let's remember, therefore we have when SI equal to 0, GIX equal to 0. We are getting when SI not equal to 0, we have what? We have lambda I equal to 0 combinedly. Let us combine these two. Combining these two, what is the condition now? Lambda I into GI of x equal to 0. This is one part. Lambda I into GI of x equal to 0. This is another part. Hence, lastly, after simplifying, thus, if you see, no need of this derivation, but you have to remember the following Kuhn-Tucker conditions. That is very important. Thus, the Kuhn-Tucker conditions. To optimize. Kuhn-Tucker conditions to optimize means maximize or minimize the NLPP, the given NLPP. Remember, in the given NLPP, what are the constraint type? Less than or equal to R. Now, this is very important. First condition is what? I will write this one also. Dou L by dou xj equal to 0. Dou F by dou xj lambda I into dou gi by dou xj equal to 0. This is I equal to 1 to m, and this is j equal to 1 to n. That's the first condition, first Kuhn-Tucker condition. And second one is what? I got already this one, lambda into GIX equal to 0. This is I equal to 1 to m. This is second Kuhn-Tucker condition. And the third Kuhn-Tucker condition is the given constraints. Already I got this, less than or equal to 0, I equal to 1 to m. And the fourth Kuhn-Tucker condition is the Lagranges multipliers are greater than or equal to 0, I equal to 1 to m. These are the Kuhn-Tucker conditions. You have to remember this compulsory. These are the Kuhn-Tucker. See, or I am writing. These are KT conditions. For what problem? Maximize z equal to f of capital X, subject to g of x less than or equal to 0 and x greater than or equal to 0. Okay. See, remember all of you, constraints are less than or equal to and objective function is maximization. Then these are the Kuhn-Tucker conditions. The main part is this. These are Lagrange's multipliers are greater than or equal to 0 for maximization less than or equal to constraint. Now, see the note. Note, if the problem is minimization, if the problem is objective function is minimization or constraints are of the form gi of x greater than or equal to 0. What is this? gi of greater than or equal to 0. Then in any one of these cases, what is the cases? If the objective function is minimization or constraints are greater than or equal to type, then these Lagrange's multipliers are less than or equal to 0. Lagrange's multipliers are less than or equal to 0. Done. These are the Kuhn-Tucker conditions. Any doubts? This is the derivation part. Necessary Kuhn-Tucker conditions. These are necessary Kuhn-Tucker conditions. Now, one more point. The point is the Kuhn-Tucker necessary conditions. The Kuhn-Tucker necessary conditions for the problem maximization of z equal to f of x subject to gi of x constraints are less than or equal to 0 and x greater than or equal to 0 are also sufficient if, what is the condition here? Objective function f of x is concave and constraints are convex and gi of x are convex functions. As I already told you how to check convex and concave function in our previous class. You find the Hessian matrix. Okay, for example, for f I have to consider what? All the first order partial derivatives, right? Dou square f by dou x1 x2 and so on. Okay, this matrix, and consider the principal minors, first principal minor, second principal minor. If all are positive, the matrix is positive definite. When matrix is positive definite, the function is convex function. Whenever convex function is there, then it possesses minimum value. If the principal minors are alternately negative positive, then it is negative definite. Then function is concave function. Whenever concave function is there, then problem has maximum value. Remember, concave function already explained. Behavior, the shape of the concave function will be like this. This is concave function, so max value simply. And convex function, this is minimal value. This is convex function. This is concave function. Okay, concave function possesses maximum value. Convex function possesses minimum value. Now, if theory is clear for you, I will go for the problem. Any doubts? Just I'm scrolling once again. If any doubts, you can raise the questions in the concept. I'm considering objective function. In particular, one can take this one as maximum, standard notation. Okay, maximum of z equal to f of x, constraints are less than or equal type only. Okay, we convert less than or equal type to equality type by adding squared slack variables. Then problem becomes nonlinear programming problem with equality type constraints. Okay, so I can apply Lagrange's function, Lagrange's method. I define the Lagrange's function. The necessary conditions for optimize are, these are the L partial derivatives, Lagrange's function partial derivatives with respect to unknowns equal to 0. Then Okay, and I am simplifying all these equations. I got the necessary Kuhn-Tucker conditions. These 4 conditions are necessary conditions. And when these necessary conditions become sufficient, when the objective function is concave and the constraints are convex, then the stationary point, whatever the point after solving those 4 sets, okay, at that point f of x is concave, then it will possess maximum value. Okay, this is the theory. Now, problem, find the optimum value of the objective function of the NLPP maximize z equal to 12x1 plus 21x2 plus 2x1x2 minus 2x1 square. Okay, space is not enough. Let me write again. Maximize z equal to 12x1 plus 21x2 plus 2x1x2 minus 2x1 square minus 2x2 square, subject to the constraints. This is not such that, subject to the constraints. x2 less than or equal to 8, x1 plus x2 less than or equal to 10, and x1 x2 greater than or equal to 0. x1 x2 greater than or equal to 0. Okay, this is nonlinear programming problem with the 2 constraints. What are the constraint type? Less than or equal to. Constraints type less than or equal to. So first convert them to equality type. Here, what is the objective function f of x? What is the objective function f of capital X? Nothing but x1 x2 equal to 12x1 plus 21x2 plus 2x1 x2 minus 2x1 square minus 2x2 square. This is our first constraint. And coming to what is the first objective function? What is the first constraint? g1 of x1 x2 is nothing but what? x2 minus 8. Take this 8 this side. Another one, x2 g2 is nothing but x1 plus x2 minus 10. x1 plus x2 minus 10. These are the constraints. g1x, g2x less than or equal to 0. Next, to convert less than or equal to type constraints into equality type constraints, add squared slack variables. Since there are 2 constraints are there, okay, I have to add s1 square, s2 square in the constraints. Then we have, what is the constraint? Then we have g1x plus, I will write like this, g1 of x1 x2 plus s1 square equal to 0 implies x2, what is this? x2, I will write, okay, x2 minus 8 plus s1 square equal to 0. g2 of x1 x2 plus s2 square equal to 0 implies x1 plus x2 minus 10 plus s2 square equal to 0. Therefore, the NLPP is, what is this becomes? F of x1 x2, objective function is maximization, 12x1 plus 21x2 plus 2x1 x2 minus 2x1 square minus 2x2 square, subject to constraints becomes what? x1 plus s1 square minus 8 equal to 0, right? x1 plus x2 plus s2 square minus 10 equal to 0, and x1 x2 greater than or equal to 0. No need to write s1 s2 because they are taken as squared, always non-negative. Now define. Now equality type constraints. NLPP with equality type constraints is now define Lagrange's function. Define Lagrange function. L of variables are x1 x2. Next one, slack variables are 2. Since 2 constraints are there, I have 2 Lagrange's multipliers equal to this minus lambda 1 into the first constraint, g1 of x1 x2 plus s1 square, okay, minus lambda 2 into g2 of x1 x2 plus s2 square. This is my Lagrange's function. Now let me substitute the values. This implies L of x1 x2 s1 s2 lambda 1 lambda 2 is equal to, what is the function, objective function? 12x1. Shall I keep like this only? Because everything is available. F is there, g1 is there, g2 is there, everything is available. Otherwise, let me write. Doesn't matter. 12x1 plus 21x2 plus 2x1 x2 minus 2x1 square minus 2x2 square minus lambda 1 into x1 plus s1 square minus 8 minus lambda 2 into x1 plus x2 plus s2 square minus 10. Now, this is Lagrange's function. Next one, the necessary conditions. The necessary, no need to write this one directly. The necessary Kuhn-Tucker conditions. The necessary Kuhn-Tucker conditions for the maximization with less than or equal to type constraints. The given problem is this one only, less than or equal to type constraints are. Now you have to list those 4 conditions. First condition, what is that? Dou L by dou x j equal to 0. J equal to how many variables here? Only 2 variables are there, x1 and x2. Second condition is what? Second condition is what? Lambda I into gi of x equal to 0. Okay, this is I equal to 1, 2. How many constraints? 2 constraints are there. Okay, 2 constraints. And what is the third one? The given constraints, gi of x less than or equal to 0. 1 to 2. Next, fourth condition, all the Lagrange's multipliers are greater than or equal to 0. 1 to 2. M stands for 2 here. Here, n, number of variables, that is 2. Okay, and m, number of constraints. How many constraints are there? 2 constraints. Okay, this is for your idea. Now I have to elaborate these conditions. Now, first condition. Now, dou L by dou x1 equal to 0. First condition, dou L by dou x1 equal to 0. So what is this first one with respect to x1? What is the derivative? 12 plus 2x2 minus 4x1, and x1 is here, minus lambda 1 equal to 0, and minus lambda 1 minus lambda 2 equal to 0. Is it correct, right? What is the constraint actually? Constraint given as, sorry, all of you, x2 minus 8. This is x2. So this is x2. So there is no x1 in the first type. So only I will get minus lambda 2. Okay. So I'm writing this is first one 12x1. So 12 plus 2x1 x2. With respect to x1 means I will get 2x2. Next 2x1 square, 4x1. In the first constraint, lambda 1 is not there. Lambda 2 will be there, equal to 0. Next, dou L by dou x2 equal to 0. dou L by dou x2, 21 plus 2x1 minus 4x2 minus lambda 1 minus lambda 2. Okay, so 21 plus 2x1 minus 4x2 minus lambda 1 minus lambda 2 equals 0. These are the first conditions. Done? Okay, I will write this is first equation, this is second equation. Done. Second set. Let me write second set. What is that? Lambda I into gix equal to 0. I equal to 1 to 2. That is lambda 1 into g1 of x equal to 0. That means lambda 1. What is g1 of x? First constraint, x2 minus 8. No need to, g1x is x2 minus 8. There is no slack there, right? Remember that point. Equal to 0. This is third one. This is third one. Next one, lambda 2 into g2 of x equal to 0. That is lambda 2 into what is this? x1 plus x2 minus 10 equal to 0. Fourth condition. This is about second KT condition. Coming to third KT condition, what is this? gi of x less than or equal to 0. I equal to 1 to 2. That is g1 of x less than or equal to 0. That is nothing but x2 less than or equal to 8. And that is x2 minus 8. Minus 8 will be there. Minus 8 less than or equal to 0. This is fifth one. Next, g2 of x less than or equal to 0. This is what? x1 plus x2 minus 10 less than or equal to 0. Sixth one. Next, coming to fourth condition, lambda I greater than or equal to 0. I equal to 1 to 2. That is lambda 1 comma lambda 2 both are greater than or equal to 0. Or you write like this. Lambda 1 greater than or equal to 0. Lambda 2 greater than or equal to 0. Okay, and let me write like this, because I need equations. 7th, 8th. So whatever the solution by solving these 8 equations, that solution must satisfy all the conditions 1, 2, 3, 4, 5, 6, 7, 8. We have to pick up that solution. All of you listen carefully. Here in the third and fourth equations, this is a multiplication of 2, lambda 1 into this part. That means what? Either lambda 1 0 or lambda 1 not equal to 0. Here also lambda 2 equal to 0 or lambda 2 not equal to 0. So entire solution depends on the cases. Lambda 1, whether it is equal to 0 or lambda 2 equal to 0 or both are not equal to 0 or one of them equal to 0. So there are 4 cases. We solve these equations in the following cases. How many cases? Since lambda 1, lambda 2, in the following 4 cases. Only 2 variables are there. First one, see, what is the first case? I will write both. I will take both lambda 1 0 and lambda 2 0. Lambda 1 0, lambda 2 0. Then what happens then? See, the cases are lambda 1. How you decide? Because of 3 and 4th equations, lambda 1, lambda 2 both zeros. Lambda 1 not equal to 0, lambda 2 not equal to 0. Lambda 1 0, lambda 2 not equal to 0. Lambda 1 not equal to 0, lambda 2 equal to. These are the 4 cases. All possible cases are these 4 only. So we solve these 4 cases to get the solutions. Then what is the first equation? Then equation 1 implies. What is the first equation? What we have? Lambda 1 0, lambda 2 0. So what I'm getting? 2x1 minus 4x1 plus 2x2 plus 12. Okay, that is the first equation. Equation 1 gives what? 12 plus 2x2 minus 4x1 equal to 0. And equation 2 gives similarly 21 plus 2x1 minus 4x2 equal to 0. Solve these 2 equations. That means what are the equations? Minus 4x1 plus 2x2 equal to minus 12. 2x1 minus 4x2 equal to minus 21. If I solving these 2 equations, solving these two equations, what I'm getting, multiplied by 2 this equation, x1 does add, this one cancel, this is 8, this is 2, 6x2, and multiplying this 2, so x2 6 to 54, this one 42 plus 12 54, x2 will be 9. Solving these equations, we get x2 value, I'm getting 9, and if I substitute x2 9, 18 minus 30 by 4, 30 by 4 means 15 by 2, x1 equal to 15 by 2, x1 equal to 15 by 2. Okay, and see, the point is, what is the stationary point? Stationary point is x1 x2 is equal to 15 by 2 comma 9. Now this point, listen carefully, this point must satisfy the remaining KT conditions. What are the remaining KT conditions? This 1 2 are already utilized, 1 2 already utilized, right? And lambda 1 equals 0, lambda 2 equals 0 means 3 and 4 satisfied. Coming to 5 and 6, coming to 5 and 6, see what is 5? Equation 5 is x2 minus 8 less than or equal to 8. That is nothing but x2 less than or equal to 8. Okay, at 15 by 2 comma 9, what we have? We have, what is x2 value? 9 less than or equal to 8 is false. Correct? I am substituting this point in the fifth constraint, fifth equation. That is, KT condition 5 is not satisfied. That is, KT condition, Kuhn-Tucker condition, equation 5 is not satisfied. Not satisfied. Therefore, discard the point or reject. Discard the point 15 by 2 comma 9. This is not the solution. This is not the solution. Okay. Next case. What is the second case? Let me consider case 2. Case 2. Lambda 1 not equal to 0. Lambda 2 not equal to 0. I will take this. When lambda 1 not equal to 0, lambda 2 not equal to 0, from 3 and 4, what equal to 0? This part, x2 minus 8 equals 0. And x1 plus x2 minus 10 equals 0. Then from 3 and 4, then from the equations 3 and 4, what we have? We have x2 minus 8 equal to 0. That is x2 equal to 8. And x1 plus x2 minus 10 equal to 0. That is x1 plus x2 equal to 10. That implies, what is x1 equal to 10 minus 8, x1 equal to 2, x1 equal to 2, right? Therefore, stationary point is, what is the stationary point here? Stationary point is x1 comma x2 is equal to 2 comma 8. Now let us check, this 2 comma 8 satisfies the remaining KT conditions or not? Remaining KT conditions or not? Okay. Now substitute 2 comma 8 in 1 and 2 to get lambda values 1 and 2. What is one equation? I think, what is the one equation? See, let me check. One equation is 12. What is that? 12 plus 2x2 minus 4x1 minus lambda 2 equal to 0, right? Now substitute these values, I will get lambda 2 value. Done. And what is the second equation? Second equation is 21 plus 2x2 minus 4x2 minus lambda 1 minus lambda 2 equal to 0, right? Then what about lambda 2 value? Check it. Lambda 2, this is 12. x2 value is 8. 8 means this is 16. Minus 4, this is minus 8. So what is the lambda 2 value? What I'm getting? 28. 20. It is positive. Greater than or equal to 0. Right? Lambda 2 is greater than or equal to 0. I'm getting this. Yes, it is satisfied. The last KT condition is what? All the Lagranges multipliers greater than or equal to 0. So 1 lambda 2 is greater than or equal to 0. Let us see what about lambda 1. This is lambda 1, 21, 2x2, 16. Sorry, this is not 2x2. I think 2x1 minus 4x2. This is 1. Now this is 1 means 2x1, that is 4, minus 4x2, 32, minus lambda 1 minus 20 equal to 0. Now we'll keep lambda 1 onto the, take lambda 1 onto the right side. This is 25. This is 25 minus 32, 52. That is equal to how much? Minus 27. It is less than 0. It is not. Lambda 1 equal to minus 27 is not greater than or equal to 0. That is, what is this condition? Lambda 1 greater than or equal to 0 condition, KT condition, seventh one. So that is KT condition equation 7 is not satisfied. Therefore, reject the point. That means this case is also discarded. Reject the point 2, 8. Now, third case. Case 3. What is the case 3? Case 3 is take either one equal to 0. Lambda 1 not equal to 0 I am taking, and lambda 2 equal to 0. Lambda 2 equal to 0. Done? Now, one by one, let me solve. When lambda 2 equal to 0, equation 1 implies, already I have written here, equation 1, yeah, 12 plus 2x2 minus 4x1. 12 plus 2x2 minus 4x1 equal to 0. This part is over. Now, when lambda 1 not equal to 0, from equation, I think lambda 1 na? Yeah, lambda 1 not equal to 0 means x2 minus 8 equal to 0. So that, what is that equation? Third equation. So from equation 3, we have x2 minus 8 equal to 0. That is x2 equal to 8. So from this, what is this gives? This gives 12 plus 16 minus 4 equal to 4x1. So x1 equals to, this is 28. x1 equal to 7. Is it correct? Sorry. 12 plus. Wait. Equation 1 is correct. 12 plus 2x2 minus 4x1, right? Lambda 2 0, correct? And x2 equal to 8. x2 equal to 8 means this is 16. 12 plus 16, 28. Is it correct?
Yes, sir.
Yeah. x1 equal to 7. Therefore, stationary point is what? Stationary point is x1, x2 equal to 7, 8. Now, with this, I have to find lambda 1, lambda 2. I have to find lambda 1, lambda 2. What is the equation 2 implies? Substitute this one in equation 2. 2 somewhere, yeah. 21 plus 2x1 minus 4x2. 21 plus, just wait, second equation, 21 plus 2x1 minus 4x2 minus lambda 1 minus lambda 2 equal to 0. Already I know lambda 2 equal to 0. I have to calculate lambda 1. So this is 21 plus 2x1 means 14 minus 4x2, 32 minus lambda 1. Lambda 2 is 0. So what about lambda 1? This is 35. 35 minus 32, that is 3, greater than or equal to 0. Lambda 1 is positive, right? Any corrections? Yes? Two x1, right? Lambda. Now, what are the constraint next one? So, with 7, 8, lambda 1 equal to 3, lambda 2 equal to 0. What the remaining KT conditions? Now we have okay, remaining KT conditions we have, see, already I have taken third and fourth verified. I have to take fifth and sixth. Fifth and the sixth, x2 minus 8 and x1 plus x2. I have to satisfy those two conditions. With the KT conditions 3, 4, 7, 8 are satisfied. 1, 2, 3, 4 are satisfied. Now, what is this one? Fifth condition. What is the fifth KT condition? x2 minus 8 less than or equal to 0. What is x2 value? This is 8 minus 8 at 7 comma 8. 8 minus 8 less than or equal to 0. 0 less than or equal to 0. True. Means satisfied. Next, sixth equation implies. What is that? x1 plus x2 minus 10 less than or equal to 0. So x1 7 plus 8 minus 10. Appo ikkada fail avutunda, less than or equal to 0. This is 15 minus 10. 5 less than or equal to 0 is false. Is false. Therefore, sixth KT condition, equation 6 KT condition is not satisfied. Is not satisfied. Therefore, discard this case. Discard this solution. Therefore, discard this solution. This solution is also rejected. Any corrections? Last case, fourth case is there. Case 4. What is that case? Lambda 1 equal to 0, lambda 2 not equal to 0. Right. Now when, which equation? Yeah. When lambda 2 not equal to 0, equation 4 implies x1 plus x2 minus 10 equal to 0, correct? So x1 plus x2 equal to 10. One equation is I got. Next one, when lambda 1 equal to 0, equation 1 implies. When lambda 1 equal to 0, equation 1 implies. What is the 1? 12 plus 2x2 minus 4x1. Lambda 1 0. Lambda 2 will be there. So minus lambda 2 equals 0. And equation 2 implies 21 plus 2x1 minus 4x2. Lambda 1 is 0. So I will get minus lambda 2 equal to 0. Lambda 1 is 0. So lambda 2 I am getting. Done. Now these three equations I have to solve. I have to solve these three equations. For the three unknowns. What are the unknowns? x1, x2 and lambda 2. x1, x2 and lambda 2. This is one equation. So I'm taking underline. This is one equation. This is another one. This is another one. So how to solve this? Let me check. This implies, what is the first equation? Minus 4x1 plus 2x2 equal to lambda 2 minus 12. Next equation is what? 2x1 minus 4x2 equal to lambda 2 minus 21. And another one is what? x1 plus x2 equal to 10. Any idea? Yes? Any idea? One thing. From these two equations, eliminate x1 and get x2 in terms of lambda 1, lambda 2. Done? Otherwise, and get x1 and x2 in terms of lambda 2 and substitute in this equation. That's better. Otherwise, shall I substitute this one lambda 2 value here? Then yeah, better. See, from this equation, lambda 2 equal to, let me take all of you. I'm taking this as A equation and this as B equation and this as C equation, right? Okay, just for an idea. From B, what is lambda 2 equal to 2x1 minus 4x2 plus 21, right? Then put in A. Then A implies minus 4x1 plus 2x2 equal to 2x1 minus 4x2 plus 21 minus 12. So what is this in terms of x1 and x2? Take this entire into left side. This is 12. This is 12. This is minus 6x1, isn't it? Minus 6x1 plus 6x2 equal to 21 minus 12. How much? 9. 9. And C equation. What is the C equation? X1 plus x2 equal to 10. So I will write minus x1 plus x2 equal to 9 by 6. And here x1 plus x2 equal to 10. If I add these two, I am getting 2x2 equal to, adding 2x2 equal to 9 by 6 plus 10. That is 69 by 6. So x2 equal to 69 by 12. x2 equal to 69 by 12. That means 3 2s are 3 3s are 3 4s are 23 by 4 x2 value. Then x1 plus x2 equal to 10 implies x1 equal to 10 minus x2. So 10 minus 23 by 4. Done. So what is x1 value? 40 minus 23. 40. That means 17, I think. 17 by 4. Okay. And what is lambda 2? I need to get lambda 2 also. What is lambda 2? And lambda 2 equal to, I got this expression now. 2x1 minus 4x2 plus 21. 2x1 minus 4x2 plus 21. Isn't it? Yeah. Now substitute here. 2 into 17 by 4 minus 4 multiplied by 23 upon 4 plus 21. This is lambda 2 value. So this is 34 minus, this is 12, 92 plus 484 whole by 4. Whole by 4. So what is this value? 84 plus 34, 8. 1 1 minus 92, that is 6, 26, isn't it? 26 by 4. 26 by 4 means what? Lambda 2 equal to 13 by 2 greater than or equal to 0. Therefore, the stationary point is, what is the value? Stationary point 17 by 4, 23rd by 4 with lambda 1 is 0 and lambda 2 is 13 by 2. Now, I got the solution. I have to check the remaining KT conditions. Now, KT condition, what is the condition? 5. KT condition 5 implies x2 minus 8 less than or equal to 0. What is x2 value? 23 by 4 less than or equal to 8. Is it correct? Yes, is true. Next, KT condition 6. KT condition 6 implies x1 plus x2 minus 10 less than or equal to 0. So what is this? 17 plus 23 by 4 less than or equal to 10. That implies this is what? 40 by 4. 10 less than or equal to 10 is also true. And lambda 1 equal to 0, lambda 2 equal to 13 by 2 greater than or equal to 0 satisfies what KT conditions? Last KT conditions. KT conditions 7 and 8. 7 and 8. Hence, last conclusion. Hence, the stationary point. What is that point? 17 by 4, 23 by 4 satisfies all the KT conditions, all the Kuhn-Tucker conditions. Okay, this point is over. Hence, Hence, it is considerable. Hence, it is considerable. This point is considerable. Now, the question is whether this stationary point gives maximum to the objective function. Question is what? NLPP objective function is maximization, right? Now we have to check. Now we have to check whether this point 17 by 4 23rd upon 4 gives maximum to the objective function. Maximum to the objective function. Maximum to the objective function. What is the condition? For this, we have to check. Already told you sufficient conditions. For this, we have to check the maximum function means what? Concavity of the objective function. Okay, so what is the objective function? F of x1 x2 is equal to, what is that function? Function is 12x1 plus 21x2 plus 2x1 x2 minus 2x1 square minus 2x2 square. For this, yesterday's class, Hessian matrix. The Hessian matrix of f of x1 x2 is, the Hessian matrix of f of x1 x2 is h of x equal to second order partial derivatives matrix, dou square f1 by dou x1 square, dou square f1 by dou x1 x2, dou square f by dou x2 x1, dou square f by dou x2 square. Since two variables are there, it is 2 by 2 matrix, right? Now, what is with respect to x1? 2 times now. One time 12 is there, second time 12 will not be there, and 2x2 will be there. Here minus 4x1, so minus 4 will be here. Minus 4 will be here. Let me write for clarification. Dou f by dou x1 is 12 plus 2x2 minus 4x1, and dou f by dou x2 is 21 plus 2x1 minus 4x2, and one more derivative now for this. Now dou square f by dou x1 x2 means dou f by dou x1 derivative with respect to x2, then 2 will be there. Next one, dou square f by dou x2 x1 with respect to x1, 2 will be there, and one more derivative with respect to x2, minus 4 will be there. Minus 4 will be there. Done. Now, what is the first principal minor? Delta 1, that is more determinant of this, minus 4. Minus 4, negative. Not mod 4, this is determinant. Delta 2. Delta 2 means what? The determinant of 2 by 2 minor. That is what? 16 minus 4. That is 12 greater than 0. Since delta 1 less than 0, delta 2 greater than 0, alternately, yesterday I told you, no, alternately negative and positive. Negative and positive. The h of x is negative definite. H of x is negative definite. Hence, when negative definite means the function is concave function. Concave function. Hence, it has maximum value. It has maximum value at what stationary point? Stationary point is what? 17 by 4, 23rd by 4. And one more important point, I have to evaluate the stationary point at 17 by 4, 23rd by 4. Anyway, we are getting constant values. Doesn't matter, right? Maximum value, this one. Therefore, maximum of f of x1 x2 is equal to, now substitute in the objective function, 12x1 plus 12x1 plus 21x2, and what is the function? Plus 2x1 x2, 2, 17 by 4, 23rd by 4 minus 2x1 square minus 2x2 square. Evaluate this is the function. That's enough. And one more point here, since the constraints are linear. Linear means what? There is no square terms. x2 less than or equal to 8, x1 plus x2 less than or equal to 10. Those are linear. Constraints are linear. They are always convex functions. They are always remember, linear functions are convex as well as concave, because straight line. Linear function means what? Straight line. It possesses maximum value and a minimum value. That means same constant value. So linear functions are always convex functions as well as concave functions. Okay, just find this value. Don't write find in examination. Find this value. Okay, this is Kuhn-Tucker condition. Any doubts? First, I explained clearly the method, Kuhn-Tucker conditions method for a inequality type constraint, the method, and we have 4 Kuhn-Tucker conditions. Okay, and coming to problem, same applied the method as usual. Coming to the problem, objective function, first I have written G1, G2, the constraints, then convert them to equality type constraints by adding squared slack variables. Then problem becomes equality type NLPP, define the Lagranges function. Then immediately you write, no need to again write all those equations. Directly you put on the necessary Kuhn-Tucker conditions directly, 4 Kuhn-Tucker conditions. Now you have to simplify these 4 Kuhn-Tucker conditions. One by one I have taken. One, in first KT conditions we have 2 equations. In second KT conditions 2 more equations. Third KT conditions 2 more. And fourth KT conditions 2 more. Now since because of equation 3 and 4, lambda 1 equal to 0, lambda 2 equal to 0, or not equal to 0, or one of them may be 0, there are 4 cases arise. These 4 cases, lambda 1, lambda 2, 0, both not equal to 0, and one of them will be 0. So I deal with 4 cases. In case 1, I got one solution. Whenever after getting the solution and the lambda 1, lambda 2 values, you put on those values in the remaining KT conditions. If it is said all the conditions are satisfied, yes, the point is considerable. Otherwise, reject it. First case is rejected. Similarly, second case is also rejected. Third case also rejected, because some of the KT conditions are not satisfied. See, in the third case, the 6th KT condition, x1 plus x2 minus 10 is not satisfied. So reject that one. But coming to 4th case, after getting the stationary point and lambda 1, lambda 2 values, and I checked the remaining KT conditions, every KT condition is satisfied. Hence, it is considerable. Now, after this last point, I have to check whether this point is really giving maximum value or minimum value. For that, I have to check the concavity. For a maximum, concavity. For a minimum, convexity. To decide concavity, convexity, we have to write Hessian matrix of the objective function. What is the Hessian matrix? Second order partial derivative matrix. I have written, and evaluate this matrix at the given stationary point. Same constants are there, so remains constants as. And delta 1, first principal minor, determinant of -4, that is -4, negative. Delta 2, positive. Alternately negative, positive means Hessian matrix is negative definite. Then function is concave function. Yes, since it is concave, it possesses maximum value. I calculated maximum value, and obviously whenever the constraints are linear, definitely those are convex. So sufficient conditions also satisfied. What are the sufficient conditions for maximization? Objective function is concave and constraints are convex. Okay, this is the problem. Any doubts? Okay, I will give one problem assignment for you. Try to solve this. And I will stop here. Solve the NLPP. Maximize z equal to minus x1 square minus x2 square minus x3 square, 3 variables, plus 4x1 plus 6x2 subject to the constraints x1 plus x2 less than or equal to 2, 2x1 plus 3x2 less than or equal to 12, x1 x2 greater than or equal to 0, x1 x2 greater than or equal to 0. And I will give the solution. X1 equal to answer x1 equal to 1 by 2, x2 equal to 3 by 2, x3 equal to 0. Since two constraints are there, we have two lambdas. Lambda 1 equal to 3, lambda 2 equal to 0. Okay. If you solve this problem, if any doubts, it will be clarified for you. Okay. Any doubts?